Okay, so I'm uh, I'm gonna call it. Uh, we're going to there was a test four review that we did for test four, but I'm gonna skip over that review. So everything that was for test four, we did that review in class. It's been posted. I'm not going to go over that review. So we are now going to do our. This will either be the final. Set timer for 55 minutes. This will either be the final part, or it'll take me two to get through this. But so we are either going to have part 7 and 8, or we're just going to have part 7. Anyway, this is the last review. Um, so, what do we have? Lambda equals, if we multiply by the frequency times the wavelength, is going to equal our C. And that gives us lambda in meters. So the lambda is what resonates with things. And I don't know why you wouldn't want to just read about this, because what I've written there is probably the best thing. But at any rate, we can go 10 to the 8, 10 to the 7, 10 to the 6 meters in length for an object. That's quite a large object. And that would be the range there, all the way down to 10 to the minus 16, 10 to the minus 17, 18 meters. That's pretty small, but that's a very wide range that we can cover with the electromagnetic spectrum. So now we do the same thing with sound waves and all that other stuff, and we get ultrasound imaging and everything because of the computers. But we're just going to stick with E&M for now. And we're going to get to... I'm going to skip over the historic stuff. And let's just go straight into writing Maxwell's equations. Okay, so we've got one law. We've got two laws. We've got three laws. We just talked about that one, Faraday's. And oh, I almost wrote something wrong. So that change in magnetic flux with respect to time is also a way, this is another way to generate our B field. So these are the three laws. We've got two Gauss's laws. So we got two Gauss's laws. The first one for the E field, the second one for the B field. And then we've got Faraday's. And then we have Ampere-Maxwell. This is the Ampere part. This is the Maxwell part. The Ampere-Maxwell equation. I have crackers and cheese, but I don't want to talk and chew crackers at the same time. That has no class. So let's not do that. So we've got these equations. This field equations describe E and M completely. We've got everything we need to know, and now we can take these allow us to find E and B. Okay, given all the things that we know about the situation, we might have an initial current. Who knows? For whatever you want to do, whatever the situation is, you can come up with and get your E's and your B's out of those equations. So you get your E's and your B's, and what do you do with them? Well, you use Lenz's law, Lorenz's force law. We are combining the two forces because the Lorentz force law is the Lorentz E for an E field and the B for the B field, and all we've done is, or all Lorentz did, was say, well, this is one force, this is the other force, let's put them together and call it one force. And so Lorentz does that. And through the fact that F equals ma, that allows us to start getting, from there we can start figuring out our velocity and then our position. Okay, so we have our acceleration, we can figure out our velocity and position. So by just equating F F Lorentz to Newton's F equals ma. All right. So that's pretty cool. What else do we have here? Let's see. Okay, so I guess we're going to talk about Gauss's laws and what are the meanings. Well, first of all, this first law means, disregarding the constant, this little constant here, disregarding that, you're essentially saying I've got some source charge, okay? This is the monopole for the E field. Well, it's just a source charge. And a monopole, it's quantized, so it can only be E plus or minus. That is the quantization of our electric charges, and that's as small as they go, and so therefore we can go all the way down to those little bitty charges as our Q inside the closed surface. So that's it. That just says we've got monopoles. we've got charges that are monopoles. But for the B field, there are none. Zip, zero, no monopoles. Okay, so that's our discussion about that. We don't even need to debate it. Don't even trip. No monopoles in a B field. So now let's talk about our E field. And this is an induced E field, okay, because Gauss's law initially says our E field will be as a result of the charge enclosed. Okay, so that's our initial way of getting an E field. Our induced way of getting an E field would be the change in the magnetic field. The flux, actually, the change in the magnetic flux, however you want to do it. That's our Faraday's law. And so we're getting an E field here that is induced. That's induced from the change in the magnetic flux, okay, in time. All right? So we've now got two ways of finding an E field. Now, our B field doesn't have an initial way to get its, because there's no monopoles. It only happens as a result of a charge, a moving charge, right? A flowing charge. Well, our flowing charge is called I, and it's a current. So our mu naught times our current, mu naught's just the little constant. The current's the thing, and we've got our current flowing, and that generates our B field. Okay, great. Now, there could also be a change in the electric flux in time, and if that's happening at the same time as this current, fine. Then you add them together and you get your B field. However, oftentimes we've got the current that starts us out, and then gradually the only thing that we have left as we propagate out away from the current is the electromagnetic radiation rotating back and forth, and that is going to be our change in the electric field. It's speeding away at some velocity c, and that's our quote-unquote induced B field. We didn't distinguish between induced B field and regular B field because the B field is essentially always induced at all points because there is no magnetic monopole. So a B field is something that has been induced. So that's our last statement that sums it all up, closes the feedback loop on our electromagnetics. I'm going to restate just so that we have it. The square root of mu naught epsilon naught. So just you got to keep that in mind. All the relationships that we do for these things we need to keep these things in mind. Maxwell published his equations 1862. Heinrich Hertz did his thing to test the equations in 1887. It's called a spark gap transmitter, what he did. And you can look them up. I think they may even still have his original spark gap transmitter in a museum somewhere. I don't know. Maybe I'm wrong. Might probably be making that up. But at any rate, Hertz did a great thing with his spark gap transmitter. The equations, however, that we need to know for an RLC circuit are these, of course, and then I'm going to write it again, equals C, but C also equals 1 over the square root of mu naught epsilon naught. So those are equations that we get. So let's move on to plane waves. And our plane waves, doesn't matter what your function is, so you take the derivative twice with respect to x, you take the derivative twice with respect to t, and low and below, when you do that, you end up with 1 over c squared times the t term. And if you were to do that with an electric field, you would find that c squared is equal to 1 over mu naught epsilon naught. So that's it in a nutshell. Energy in E&M waves. So we had two energies before. We had 1/2 epsilon naught E squared for the E field when we were studying that, and then we had the B field. We had 1/2 1 over mu naught B squared. It turns out that because it's two different ways of looking at the same field, those two things are equal. And also the total energy, if you were to add them together, you get your total, right? So they're equal, but also this is true too. So the combination of them being equal and being able to add them together gives you a bunch of equations that you could have. You could have this. You could have this. And you could combine them, and you could do, where's my third one? Yeah, 1 over mu naught E B, and I think we need to divide by 2 times 1/2. Does that work? I think that's it. Yeah, I think that's it. Why are we dividing by 2? No, that is not it. That's not it. To do it right, I think we need to divide by C. So that's not it. But what is true is our pointing vector S, which we can go through and figure out, but let's just write out what S is. 1 over mu naught times E cross B. We're always going to find that E is perpendicular to B, which means the sine of the angle between them is always going to be 1. So we can just write it like this. And if we were to take the average, I did it in class, the average, then we end up basically with 1/2 1 over mu naught. So 1 over 2 mu naught EB. And that turns out to be our intensity. So it's a thing that we call intensity. So now that we have intensity, and we know that it's 1/2 of what S normally would be, so let's do a chain of what S is equal to. It's equal to U times C. Well, U times C is just this, or C times 1 over mu naught B squared, or 1 over mu naught EB. And that's where we get the one I wrote above, I think. Okay, so then you want the average of it. You just divide by 2. And that average gives you a bunch of intensities. So everything here, if we were to multiply 1/2 by everything there, all of that equals our intensity. Every single one of those divided by 2 equals our intensity. So let's get into some power. If we notice that power is equal to the intensity times the area, then power over area is equal to our intensity, and then we can write our intensity out however we want to. 1/2 C epsilon naught E squared, for example. And it's going to be our maximum. So yeah, so that's our power. And we can do anything we want with this. We can solve for area if we're given power in the Emax. We can solve for power if we're given the area in the Emax. We can solve for Emax if we're given the power and the area. So there's a lot of stuff that can be done with that equation. We noticed in class that we had the Lorentz force law pushing on objects. There were 2 different kinds of pushes, and I really like my development. I like this better than what we did in class because it shows actually that when you have a purely absorbing material, it purely absorbs the light, and what happens as a result, the momentum changes that happen as a result. This is a very good treatment of what happens when we have a great perfect absorber. And all we're using is the impulse equation, which you guys learned about in first semester. So I really like this. So let's, I guess instead of talking about it, let's really talk about it. Impulse equation. So what do we have? We've got some particle here, and we've got a gamma, a photon, coming in. The photon hits the particle. It's completely absorbing, right? So that means it's an inelastic collision. Absorbs completely. So our force from momentum is equal to delta P over delta T, which is our P final minus our P initial. Okay, and I did it did I do it? I didn't. I'm just stating this. Anyway, this is, I did it in class, but I'm doing it again here. But this is just Planck's constant. Planck's divided by the wavelength. Okay, so yes, quantum mechanics a little bit. That's fine. If you need to have Planck's constant given to you, it'll be given to you. I don't think we're going to get into this, but what this does demonstrate for us is that when we are absorbing, so we're a perfect absorber, then our P final coming in and our P initial are definitely different. So our P initial going in is here, and our P final is 0. So our P initial going in is the only thing that happens, right? And then we've got a transfer of momentum to the particle. And then the particle, because of conservation of momentum, the particle is going to move backward. So this is a perfect absorber. So let's actually figure out what that force is. So we've got, let's just call it P naught, because we can drop the minus signs. Delta T, and delta T, because of x equals Vt, delta T is equal to lambda over c. So we've got h over hc over lambda squared, because delta T is lambda over c, because x equals Vt. Okay, so hc over lambda squared, and that's our force. When we have a perfect reflector, then our F is equal to P final minus P initial over delta T. But this time, what has happened, our gamma is going in with P initial. It hits our perfect reflector and bounces off. And it's perfect reflector, so our P final is equal to minus our P initial. So we end up with minus 2 P initials over delta T. Straightforward, no hand waving at all. This is where our factor of 2 comes in. And that gives us a force then is equal to 2 times hc over lambda squared. All right, so I wanted to show you guys where that factor of 2 comes in, not just kind of say 1 for the kick and 1 for the hit and all that other stuff. So yeah, we are left with that momentum transfer. What does that do to this particle? It means that that particle also gets that much momentum transferred to it. Okay, so the particle itself, because of the conservation of momentum, has to go screaming off with 2 times P naught. Which, since it's a massive object, isn't going to be a whole bunch anyway. Photons being massless, they don't impart a whole bunch of momentum. They do, though. There is some. It's visible. It's an observable thing. So let's look at that P radiation in terms of the things that we know of, not these quantum mechanical terms. We want to look at it in terms of the P rad, pressure of the radiation, in terms of the U that we came up with earlier. Okay, and that essentially is equal to our intensity divided by C. Okay, so this is a perfect absorber. It's going to be 2U for the perfect reflector, and that's 2 epsilon naught, and all the other ones that are equal to it. I'm not going to write them all out again. But there's a whole bunch of things that are equal to these, right? And you can just keep them normal. It would be a perfect absorber. Multiply by 2, and you've got a perfect reflector. I got a little note here. The E equals H nu, HF, I mean. That's Einstein. So Einstein did this. You can do a bunch of stuff with that, but you can end up showing that the U is equal to the momentum of the gamma times C. And that is, that's a cool equation that actually is a lot more complicated equation. When you have a massive object, it ends up being a lot more complicated. But it boils down, when you don't have any mass, you lose a term or two, and you can take the square root, and next thing you know, you've got your energy is equal to the momentum of the gamma ray times, of the photon, times your speed of light constant. So that's it. Thank you guys so much. Good luck on the final. I appreciate everything you guys have done this semester. So I think you've come a long way.